We're going to continue our conversation about neurons. We just said that the dendrites receive the information, process goes into the soma, and then eventually goes down the axon, starting at the axon hillock. So what we want to look at now, I've got a picture of an axon right here that does not have those myelin sheaths on them, so we're not seeing that. So we want to look and see what is happening with the neuron that is not firing a signal. What does it look like for a neuron to be at rest? So I got this next image here, and so this that we're looking at here is the axon. So this is the axon here, and we've got those little lipid bilayers, and we've got these proteins that are going to be through that. So that's what you're seeing here. And so out here is outside of the cell, outside of the axon. This is outside of the axon, and this is inside the axon. So you kind of have to understand that before we move on. So we're going to talk about terms of extracellular fluid and intracellular fluid. So in here is intracellular fluid. Let me get here. So inside is intracellular fluid. That's inside of the axon or inside of the cell. This is intracellular fluid. And so for now on, I'm going to be abbreviating that just to make it as ICF. And then outside would be here and out here. That's called extracellular fluid, which is outside of the cell. And so this would be ECF. So we're talking about the fluid inside and outside. This would be also ICF. So ECF is also over here. So we've got outside. So what we've got going on here, and I've colored mine, so you might want to pause and color. You don't have to, but I've colored mine to let you see that we've got a bunch of different protein channels, and those are going to play a part in what's going to be going on. So we are right here at the axon hillock. So I'm going to put AH. Axon hillock, that is that trigger point. That's the important thing going on there. And so along the axon, we are looking at an axon here. Let's go ahead and label that. We're looking at this as the axon. Okay, so this is the membrane that is around the axon. You've got a bunch of different channels, and we're going to look at 5 in particular, and I've just got them randomly set throughout, so I just doubled them, but this is 1 here, so this we'll just call this one 1, and we'll call this one 2, and we'll call this one 3, and this one has an A and a B part to it, so we'll talk about that one. This is number 4, and I know this one and this one look similar, and then this is our number 5 here. Okay, so first thing I want is to add something to this one. I'm going to add like a lid, and I couldn't do this because I wanted to use the same drawing. So I want to like a lid that would close. So I'm going to put a lid on this to say that this one is closed. And see, this one's got a space too. This one's also closed. So we've got this one closed to the outside and closed to the outside. That's important. Okay, and then I'm going to do one more thing right here. I'm going to put ATP on this one. It would go on all these that have this 2 and 3 thing. ATP. ATP. All right, so ATP. All right, you ready to begin? Let's begin. So all of these that are like that, I'm just going to label them all. So what we've got at number 1, so if you want to come down, I'm going to tell you what we got. So what we've got at number 1 is we've got a sodium channel. And so I've drawn it where it's really close together. And so that's going to allow some sodium to move it. But what it is, it's called a non-gated sodium channel. And what we call is a leaky channel. Have you ever had like a leak? Leak just lets a little bit in. So this is a passive transport. So this one, number 1 and number 2, I drew them really close together because it just allows some some of the ions to leak through. So they're not going to be our big players. I just drew them there. They don't necessarily have to be right there, but they do have them all through the chain. So number 1, and we've got that in that turquoise color there, it is a I don't know if we can see that color. Let me try that again. So what we have on number 1 is a non-gated, which means it's not totally closed, but it is a leaky because it means it's going to let some seep through. Sodium ion channel. Sodium is Na with a +1 ion channel. So it's allowing sodium to leak one direction through the membrane. So we'll come back and talk about which way it's leaking in just a minute. And our number 2 is also a non-gated, leaky, but this one's a potassium channel. So all the pinks we've got are potassium, and all the turquoise are sodium channels. And because they're leaky channels, they are passive transport. What does that mean? Passive means no energy. That means just simple diffusion going on with these guys. So diffusion, remember, is no energy required. So we basically got some leaky pipes going on. And so your cell, your axon, and also your cell has sodium, potassium everywhere. So this is allowing sodium and potassium to move on this. And so what's happening with the sodium and potassium channels, we'll come back to, because we want to talk about this sodium potassium pump that's here at number 5. So at number 3 and number 4, I put those closed doors on there because they are some channels, and one is sodium and one is, let's see which one I drew first. I drew the turquoise, so that's going to be a sodium channel. So what this one is a voltage gated. So what we mean by that is it's going to take some electricity of some sort to open it. This is a sodium gated sodium channel. And it takes some voltage for this thing to open. So right now at rest, the sodium channel is actually closed. It's closed during the rest. So I'd like you to know that. So it's nothing's moving through that channel right now. But it's going to open, and this is important, opens when the voltage gets just right, and we call it a membrane potential. When the membrane potential, which is aka voltage, membrane, which is what we're looking at that cell membrane or the axon membrane, called the axolemma is what it's called. The cell membrane potential, and that is going to be the special word we use for voltage. So when the voltage reaches a certain level, and that's when we're going to learn that is -55 millivolts. So when we get at -55 millivolts, we're going to see that little guy open. So we're going to see, get that moved up, this little door is going to pop itself open if this gets to be a -55 millivolts. All right, on to number 4, and I know this is not making a lot of sense until we get going. So then number 4 here, because I've switched colors and I've put that thing on, this is also voltage gated, which means it's closed as well. That should have been gated. Potassium channel. And so it's also currently at rest. It's closed. So something must trigger it to open. Well, it's voltage gated. And so it's going to open fully. And I'm telling you this for a reason. When the membrane potential becomes a positive, becomes a positive 30 millivolts. So these are important numbers. So sodium's going to open at negative 55, potassium's going to open at positive 30. So I put open fully because this is a very slow gate. It's slow to open and it's slow to close. So it's kind of like if you've ever been like at the mall when the handicap doors, you press the button, which is what voltage gauge does, and they open very slowly and eventually they'll close. That's important for later. So these two at rest are not players because they're closed. We're introducing them because we're going to need to see them. So the other player at rest is number 5. And so number 5 is actually, because you've got, I drew some ATP on them, is something called the sodium-potassium pump. The sodium-potassium pump. And so what it does, it is a form of active transport. What does that mean? It means it takes ATP energy. Active transport, which is ATP energy, which is why I drew ATP. So it's going to take ATP energy to pump what it needs. And what you need to know is that it pumps 3 sodiums out of the axon and 2 potassiums in the axon. Okay, so that's what the sodium-potassium pump does. 3 out, 2 in. 3 out, 2 in. And it's responding to the leaky channels is what it's doing. So these beginning ones, and they're not necessarily right there. They're all down the thing. I just put them there. So you have leaky channels, and so we've got the pink one, which is the potassium. Here, let me write that on there. This is my potassium, and this one is my sodium. Let's write it in black so I can see. There we go. That way maybe I can keep up with what I've got going on here. And so what's happening with this sodium, it's leaking, but it's leaking actually into the cell. So this is causing all these that look like they're closed here. There's just this like drip of sodium. And that's why the sodium-potassium pump, which is a huge player in your muscle movement, etc., that's why it's kicking out 3 sodiums. So I'm going to draw 3 sodiums here for you can just see. Okay, this is just a tiny amount just leaking, but this is actively kicking out 3 sodiums. Well, this actually is leaking the other direction. So some potassium is just leaking out a tiny bit, all these channels. And so this pump is actively pumping in 2 potassiums. So we've got 3 things going out, 2 things going in. 3 things going out. These are just leaks, not a huge thing. 3 coming out, 2 going in, 2 coming in, 3 going out, 2 coming in. So I want you to think about your bank account. If you had your bank account, $3 going out, and then $2 coming in, $3 going out, and $2 coming in, $3 going out, eventually, wouldn't you think your bank account would become very, very negative? Because you've got 3 going out and 2 coming in, 3 going out and 2 coming in. So at rest, along this, you're getting very negative. I'm going to draw the negatives over here, but it's also negative over here as well. So very negative along the membrane. So very negative along the membrane. Also very negative here. I'm just going to run out of space. And we say that it's called polarized. Polarized means the inside is very negative and the outside is very positive. This is what polarized means. Polarized. And the reason it's very positive out here in this extracellular fluid is because I've got 3 going out and 2 going in. 3 going out, 2 going in. So this is known as polarized. I don't know where to write that. Let's see if I can scoot myself over a little bit. So this little scenario is called polarized. That's important because it means we have a negative and positive. So there's what we call a potential difference. And if we were to stick something in here and measure how much more negative this is compared to this out here, we would find that it's quite negative, and it's at what we call a negative 70. And that's an important number. It's at negative 70. So our resting voltage is negative 70 millivolts. So at rest, when the thing's not doing anything but actively leaking and pumping, I should say passively leaking and pumping, the membrane potential is sitting at negative 70. That's an average. You'll find some books say something different. So what's going on at rest? Well, you've got some things leaking. These guys are closed and this guy's pumping. There is a way to help you remember the way things are pumping, and this is important. They say salty banana. So maybe you know that this is inside the neuron, so inside the intracellular fluid. So bananas are made of potassium and salt is made of sodium. So this is what's happening. 3 of those are going out and 2 going in. So if you can remember salty banana, salt on the outside, Na on the outside, and 2 on the inside, and that is making it polarized, and that's what's going on. That's the resting membrane. That's just the beginning part of the story, because that's going to play a big role in what we're about to see when the action potential starts. I know this seems like a lot, but I promise after a little bit it'll start making sense. Okay, so I'll see you on the next video. Sorry, this one was a little long.